Hi, I'm Conrad, and I'm with Zach and Tyler, and we're going to talk about spectroscopy. Spectroscopy is a study of how matter interacts with electromagnetic radiation, or light. It is often used to determine the composition of objects, such as stars. I'm having some technical difficulties. Okay. Electromagnetic radiation. So electromagnetic radiation describes waves of light that interact with the electromagnetic force and cause changes in electric fields and magnetic fields. So the electromagnetic spectrum distinguishes light as a range of wavelengths and frequencies associated by the equation lambda is equal to the speed of light over f, where lambda is the wavelength and is usually denoted in meters or nanometers, and f is the frequency, which has units of inverse seconds, or hertz. So white light, or visible light, the light that our eyes are sensitive to, is in the electromagnetic spectrum with wavelengths of 380 nanometers in the violet to 740 nanometers in the color red. So as the wavelength of light increases, its energy decreases. The opposite is true for frequency. As the frequency of light increases, so does its energy. Gamma rays, for example, have a very short wavelength, but a very large frequency, and therefore a very high energy. Whereas for long radio waves, the wavelength is very large, and the frequency is very low, and so it has a very low energy as well. So light acts as both a wave and a particle, and this is often known as wave-particle duality. One way we know that light acts like a wave is through diffraction. Diffraction occurs when light waves go through a small opening, or aperture, and spread out like a wave. Waves also interfere constructively, adding onto each other, as you can see in this bright fringe right here, and destructively subtracting from each other, where these dark spots occur. And this is known as a diffraction pattern. So to describe light as a particle, we can look at the photoelectric effect. And the photoelectric effect can be observed by shining a light on a metal surface and observing an electric current. So what happens is light, a light particle, a photon of a specific energy, hits a metal, and that metal might require a certain amount of energy to eject an electron. In this case, what we're seeing here is the metal potassium, and it requires 2 electron volts to eject an electron. This photon has 1.77 electron volts and does not have enough energy to eject an electron. While this photon does have enough energy, and it releases a photon with a velocity of 2.96 times 10 to the 5 meters per second. This photon of higher energy releases an electron of an even higher velocity, or kinetic energy. And therefore, light can be described as a particle as well. This becomes useful when describing ionization, which I will give to Zach to describe.
Ionization is similar to the photoelectric effect. It is a word used to talk about separating an electron from a proton. Ionization is specifically used to describe the process of giving an electron a specific amount of energy, as you can see here, energy coming in to an atom, and then an electron being spit out of that atom. For this example, we see hydrogen here. Here we have a ground state. Here we have energy levels of hydrogen specifically. At n equals 1, this is the ground state of hydrogen with 13.6 eV. When an electron is given enough energy, a specific amount of energy, it can jump out of all these higher energy orders and break free from the proton. Hydrogen is the simplest element there is. It is composed of 1 proton and 1 electron. When hydrogen is ionized, the electron, as I said, gets jumped out of the ground state and is free to roam. This process is called an absorption, because an electron absorbed enough energy to enough energy to get out. However, the electron does not like to live away from the ground state. It will lose energy and fall back down to the ground state that it was in once before. When an electron does this, it is called an emission, because the electron is emitting that energy in the form of light. Both absorption and emission corresponds to two different types of spectra. As you can see here, this gas right here on the left is ionized hydrogen. It is a tube of gas, hydrogen gas, ionized through an electrical current, which then creates hydrogen to be ionized and then give off this light. Here we can see all the wavelengths of light that are given off, except for the specific wavelengths that the electron took to get out of the atom. Down below, we have the emission spectrum of hydrogen. Here we see no wavelengths besides the ones that the electron took to get out of the atom. So an emission spectra shows us what we took in only, and an absorption spectra shows us what we are left with. And for the next part, we will be talking about emission, specifically more in depth. Handing that over to Tyler.
Thank you. So to talk about this more specifically, an emission spectrum comes from when we are just observing a body out in space, so such as a star. We will see light coming back at us, and that light will peak at certain wavelengths that correspond to the elements that make up the main part of the composition of whatever we're looking at. Every element corresponds to a specific wavelength, and so we can use that to determine composition of things such as stars. And when we see it on the emission spectrum, it looks like bright fringes on a black background, because that's what we're seeing. And generally, hot and low density objects work best for this, but really almost anything will. However, for nebula and other objects that aren't hot and dense like stars, we tend to go towards absorption spectrums. And absorption spectrums are spectra that we observe when we're looking at a star that might have a nebula in front of it, and the spectrum will have gaps in it, the little black marks, that correspond to the elements within the nebula. And this is because light coming off of the star that is coming towards us through the nebula is getting scattered off in a random direction by the particles within the nebula. And so that is why we see dark spots corresponding to those specific elements. And we also see that over here on the graph as dips in their irradiance at specific wavelengths, which again will correspond to specific elements of that nebula in question that we are observing. And the objects that work best for absorption tend to be cool objects with a low density, such as nebula, gases, just general objects out in space. And that was a general overview of spectroscopy, and finally our sources. Thank you.
Cut.